Hello everyone. Now we are again here with a problem based on Jahn Teller distortion. Okay, so this problem says consider the following molecules or ions MnH2O whole 6 3 plus, NiH2O whole 6 2 plus and VCl4. The Jahn Teller effect is expected for. Okay, so we have to check these complexes. So starting with MnH2O whole 6 3 plus. So manganese is the central metal ion and the valence electronic configuration for manganese in the ground state is 3d5 4s2. Now what is the oxidation state of manganese? It is +3. Okay, so in +3 oxidation state, the valence electronic configuration becomes 3d4 4s0. Okay, so now if we try to accommodate this 4 electrons in T2G and EG orbitals, then what happens? So H2O whole 6 means it's an octahedral complex. So in the crystal field, it will be split into two sets of orbitals T2G and EG, and the electrons should be accommodated. How? We have what kind of a ligand? We have H2O, which is a weak field ligand, the aqua ligand. Okay, so H2O being the weak field ligand will give rise to high spin complexes. High spin means the electrons will be occupied singly first and then paired. It won't be paired initially. So 1, 2, 3 and the fourth electron will go to the EG orbital. Okay, so in the D4 configuration. Now you can see that EG orbital is unsymmetrically filled because we have only one electron in the two orbitals. So unsymmetrical filling of EG orbitals. And this unsymmetrical filling of EG orbitals will give rise to a strong Jahn Teller distortion in the MnH2O whole 6 3 plus complex. So this complex will show strong Jahn Teller distortion or Jahn Teller effect. Okay, now moving on to the second complex. Now the second complex is nickel NiH2O. So nickel here is in the +2 oxidation state. H2O has 0 charge. So Ni +2. Nickel in the ground state is 3d8 4s2. And in the +2 oxidation state, that will be only 3d8. And now water being the weak field ligand, if we try to accommodate these 8 electrons, then so 5, 6, 7, 8. Okay, we have 6 electrons in the T2G orbitals. So this shows symmetrical filling. All the orbitals are filled. So T2G orbitals are symmetrically filled. Then EG orbitals, we have 2 electrons in the EG orbital. Again, this is symmetrically filled. So both T2G and EG orbitals are symmetrically filled. And that is why there will be no Jahn Teller distortion for this nickel complex. Okay, now moving on to the third complex, VCl4. Now, as you can see, there are 4 ligands, not 6. So this vanadium complex is tetrahedral. Okay, so this is a tetrahedral complex, and that is why we have to arrange the d orbitals just the reverse of the octahedrals. Okay, so e orbitals lower in energy and t orbitals higher in energies. Now vanadium ground state electronic configuration is 3d3 4s2. And here what we can see, we have 4 chloroligands and one chloroligand has -1 charge. So that means vanadium has a +4 charge. So +4 oxidized vanadium will have a valence electronic configuration of 3d1. Okay, only one electron in the d orbital. And obviously this one and only electron will be accommodated in the e orbital, lower in energy. So this e orbital will be unsymmetrically filled. So e orbitals with 2 orbitals having only one electron, that kind of filling is unsymmetrical filling. So that is why E orbital will be unsymmetrically filled, and filling of E orbital unsymmetrically gives rise to a strong Jahn Teller distortion. So vanadium tetrachloride VCl4 will show a strong Jahn Teller distortion. Okay, so out of A, B, C, we have A showing strong Jahn Teller distortion and C showing strong Jahn Teller distortion. Manganese complex and vanadium complex. So what will be the correct answer? The correct answer will be option 1, A and C only, and not V. We have already seen that why this nickel complex will not have Jahn Teller effect, because both the Eg and T2G orbitals are symmetrically filled. Okay, so I hope you understood this explanation, and I hope it is helpful, and thank you so much.